In this lesson, we want to talk about polar coordinates. All right, so up to this point, we've exclusively used something called the rectangular coordinate system, or some people refer to this as the Cartesian coordinate system after the inventor. And we've worked with this guy to plot these points, or you could say ordered pairs, and also to graph equations. So I want you to recall that the rectangular coordinate system is going to feature the x-axis, which is horizontal, and the y-axis, which is vertical. Okay, the meeting point between the two is going to be right here, and this is referred to as the origin. Okay, so this is your origin. Okay, and when we specify this using an ordered pair, remember this is the x value, comma, the y value. So for the origin, it's going to be 0, comma 0, okay, because the x value is 0 and the y value is 0. Now, if I think about another point, let's just do a few. So let's say we do something like 6, comma 7. Let's say we do negative 6, comma 7. Let's say we do negative 6, comma negative 7. And let's say we do 6, comma negative 7, okay? So these are directed distances, okay, from the origin. So in other words, the first guy here, okay, or the first component as they say, the x value tells you how to move horizontally. Okay, if it's positive, I'm moving to the right. If it's negative, I'm moving to the left. So for this guy, 6, comma 7, I'm moving to the right by 6 units. Okay, so let me just circle this temporarily. And then the second guy there, the y coordinate, is telling me how much to move vertically, right? So if it's positive, I'm going up. If it's negative, I'm going down. So let me go ahead and from the origin go up by 7 units, okay? So you basically want the meeting point between the two. So you can go 6 units to the right and 7 units up, or you can go 7 units up and 6 units to the right, okay? Either way, you're going to end up at this point right here. This is going to be your 6, comma 7. And I know most of you know how to do this already, but basically we just want to recap this before we get into the polar coordinate system. Now for the next one, we have negative 6, comma 7. So that means I'm going 6 units to the left, right, because it's negative 6. And then I'm going 7 units up because it's positive 7, okay? So 6 units to the left, 7 units up. So this is my negative 6, comma 7, okay? The other one is negative 6, comma negative 7. So both are negative. So it means I'm going to the left, okay, because it's a negative 6. And I'm going down because it's a negative 7. So 6 units to the left and 7 units down. That's going to put me right there, okay? So this would be negative 6, comma negative 7. And then lastly, we have 6, comma negative 7. So this is positive for x and y is negative. So that means I'm going to the right and I'm going down, right? So 6 units to the right and 7 units down. That's going to put me right there. Okay, so this is 6, comma negative 7. All right, now let's think a little bit about something called the polar coordinate system. And to start this out, I'm just going to show you how we get the polar coordinates. So let's say I had something like the point where we have 5, comma 6. So this is as an ordered pair. Again, this is x, comma y. So starting at the origin, I know that to get to this point, I could go 5 units to the right and 6 units up. So that puts me right there. Or alternatively, I could start at the origin and go 6 units up and 5 units to the right. So basically that gives me the directed distances from the origin. We know that. But we also want to be able to write this with polar coordinates, which is going to be an r value, comma, a theta value, okay? So where does this come from? Well, essentially what we can do is we can create a little position vector, okay? So the initial point is at the origin. The terminal point is going to be at that point here, okay, with our 5, comma 6. So what I could say here is that with rectangular coordinates, you have x, comma y. In this case, it's 5, comma 6. So hey, start at the origin, go 5 units to the right and 6 units up. With polar coordinates, it's going to be r, comma theta, okay, where r is the distance from here to here. Okay, if you're thinking about this as a vector, remember the length of the vector is called the magnitude of the vector. So in this case, that's going to be your r, right? So this is the square root of 61. And then the theta here is the directed angle. So in other words, how much do I need to rotate counterclockwise? So starting from the positive x-axis, if I'm facing this way, I need to rotate by 50.19 degrees to get to this position vector. Okay, so let's say this is 50.19 degrees. This is an approximation, and I'll talk about how to get this in a moment. But essentially, I want you to see that it's just two ways to get to the same point, right? I could say, hey, start at the origin, go 5 units to the right and 6 units up. Or I could say, hey, start at the origin, okay, facing the positive x-axis, rotate 50.19 degrees, and then walk forward by the square root of 61 units, okay? So two ways to kind of do the same thing. Now, if we want to talk a little bit about where this r value came from and where the theta value came from, see here how I made a little right triangle, okay? And essentially we see that the length of this vertical leg here is given by the y value of 6, right? So this is basically from 0 to 6, so this is given by 6. The length of this horizontal leg here is given by the x value of 5. Okay, so really easy to work with this. You just use the Pythagorean theorem. So if you want your distance from here to here, or the magnitude of the position vector, the distance squared would be equal to, you would have 5 squared and then plus 6 squared. So d, your distance between these 2 points, would be equal to the square root of 5 squared is 25 plus 6 squared is 36. If you sum those two together, you're going to get 61. Okay, so the distance between these 2 points, or your r value, is the square root of 61. Okay, so that's where that came from. In terms of theta, okay, calculating that, basically for most textbooks, they're going to use the inverse tangent function. Remember, the tangent of some angle theta is y over x, okay? So in this case, your y value is 6, your x value is 5. So let's go ahead and say that the tangent of theta is 6 over 5, okay? And then because we're in quadrant 1 here, we can go ahead and just strictly use the inverse tangent function, right? So I can just say the tangent inverse of 6/5 like this is going to give me, and this is an approximation, so we'll say approximately 50.19 degrees, okay? Now, if you're in another quadrant, you have to be really careful because remember, the inverse tangent function is only going to give you something in quadrant 1, okay, if this argument is positive, or in quadrant 4, rotating clockwise, if this argument is negative. So be really, really careful. We're going to work a lot of examples today, and I'll show you how to deal with that. All right, now what I want to do is just take you through the basics of the polar coordinate system. So with the polar coordinate system, everything is going to be based on a fixed point, which is called the pole or the origin, okay? And essentially, most books are going to name this with a capital letter O. So this is our pole, okay, to get things started. From there, you're going to create an initial ray, which is called the polar axis. So that's going to be this guy right here. Okay, so that's your initial ray called the polar axis. And generally speaking, this is drawn in the direction of the positive x-axis. Now, once we have this set up, we can find a point P in the plane using the coordinates r comma theta. Okay, so we have our pole here. Okay, that's set up. We've constructed the polar axis. So now if I give you r comma theta, I can locate any point P, okay? So r is the distance from the pole O, okay, to that point P. Okay, so basically if you think about this as the vector OP, what is the magnitude of that vector? Okay, that's going to be r. And then if I think about my directed angle theta, well, this is just telling me how much do I need to rotate counterclockwise from the polar axis to get to this vector OP. All right, so what I want to do now is talk a little bit about how to convert between the polar coordinates and the rectangular coordinates. So what we did here is we just took the drawing from the last section, okay, and we just put it on top of basically a coordinate plane that we're used to, right? So the rectangular coordinate plane, you'll see that we have the pole that's going to be fixed at the origin of the Cartesian coordinate plane. And basically the polar axis is drawn to coincide with the positive x-axis, okay? So once we do this, we can obtain a few insights here, okay? So we have this point P in our plane, which can be assigned the rectangular coordinates x comma y, or the polar coordinates r comma theta. So let's say I gave you r comma theta, and I said, hey, I want you to give me x comma y. How could you do that? Well, if you consider that the cosine of theta is equal to what? Remember, I've formed a little right triangle here. So essentially, I can say that it's going to be the adjacent, which is going to be x here, okay, over the hypotenuse, which is going to be r here. Okay, so x over r. And then if I think about the sine of theta, it's the opposite, which is y, over the hypotenuse, which is r. So the sine of theta is y over r. And I didn't make that equal sign very good, okay? In each case, I can multiply both sides by r. I can solve for x or y, okay? So I can say that x is equal to r times cosine of theta. So x is equal to r times cosine of theta. Okay, so that's all you need to do to find x. And then for y, it's going to be r times sine of theta. Okay, so y is going to be r times the sine of theta. Okay, so pretty easy to go from polar coordinates to rectangular coordinates. Now, let's erase this and let's consider the other one, which is a little bit more involved. But basically, if I start with my rectangular coordinates, my x comma y, and I want to go to my polar coordinates r comma theta, let's think about that. So essentially what I'm doing here is I'm, again, returning to the fact that For r, I want the distance from here to here, okay? So if I'm given the x comma y, again, I'm just using the Pythagorean theorem. R squared is going to be equal to x squared plus y squared. So r is going to be equal to the square root of x squared plus y squared. Okay, that's all it is. So very easy to remember this. Now, the tricky one is to get theta, right? Because you have all these different scenarios you have to consider. If you're in quadrant 1, you can just use your inverse tangent function, right? Because the tangent of theta is what? It's going to be y over x. We know this already. But if I'm not in quadrant 1, then basically I need to get a reference angle, okay, using the inverse tangent function. And then from there, I need to take the appropriate action based on what quadrant I'm in, right? So if I'm in quadrant 2, 3, or 4, okay? So let's go ahead and think about a simple little example. And so what I have here is the negative of 3 times square root of 2 over 2, and then comma, the negative of 3 times square root of 2 over 2. Okay, so these are rectangular coordinates. I want to go to polar coordinates, and then I'm going to show you how to plot this on the polar grid. Okay, so essentially, this is again my x value, and this is my y value. Okay, so what did I just say? Essentially, if I want to find the r value is going to be the square root of x squared plus y squared. Okay, so that's the first thing I would do. So all I need to do, let's go the square root of, I'll put r out here, is equal to, I'll have the negative of 3 times the square root of 2 over 2, and this is going to be squared. And then plus, I've got to do this again, so the negative of 3 times square root of 2 over 2, and this is going to be squared. Let me make this a little bit longer so it's proper. And so if I think about this, I know that negative in each case is going to be gone, right? Square and negative, you get a positive. 3 squared is 9. The square root of 2 squared is 2. And then 2 squared is 4, okay? So essentially what I'm going to end up with is canceling this with this and getting a 2, okay? So you'll end up with 9 halves. So I'll have 9 halves here and 9 halves here. So basically I would have r is equal to square root of 9 halves plus 9 halves. You have a common denominator there. So basically 9 plus 9 is 18. You would have 18 divided by 2, which is going to be 9. Okay, so r is equal to the square root of 9, which we know is 3. Okay, so let me erase this from over here. Let me put this as r is equal to 3. Now, when we think about the directed angle theta, okay, this is where it gets a little bit tricky. First off, consider that your x-coordinate is negative and your y-coordinate is negative. So if you think about this on your rectangular coordinate plane, if your x value is negative and your y value is negative, you're going to the left and you're going down. So that means that theta is in quadrant number 3, okay? So let's keep that in mind. So let's do our inverse tangent function. If you have the same thing over itself, okay, and it's not 0, you're going to get 1. So basically I want the tangent inverse of 1. Type that into your calculator, and you're going to get 45 degrees. So if I'm in quadrant 3, what I want to do is I want to take 180 degrees, and I want to add my reference angle there of 45 degrees, and this is going to give me 225 degrees. Okay, so this is 225 degrees. So let's erase this. So I'll just put that these are polar. So the polar coordinates, okay, like this, would be, you would have 3 for your r value, and then your theta value would be 225 degrees. So to plot this guy, this is going to be 3, 225 degrees. On our polar grid, basically what we do, to construct this grid, remember you have your pole or your origin. Okay, let me make that visible. And essentially, this is going to be the center for everything, okay? Then you're going to have your polar axis, which again is drawn in the direction of the positive x-axis. So you have some notches here. So this is 1, this is 2, 3, 4, so on and so forth. And basically what these are going to give you, you're going to make some circles. And the first one is going to have a radius of 1, right? So basically up here, this is 1. This would be -1 if you think about it as the regular Cartesian coordinate system, and this would be -1, right? But the distance from the center or the pole to any one of those points would be 1, right? So that circle would have a radius of 1. Then you would have a circle with a radius of 2, then 3, then 4, then 5, so on and so forth. Then you also have these angles here, which are in increments of 15 degrees, or if you're working with radians, pi over 12 radians, okay? So essentially, if I want this 3, 225 degrees, I'm finding the meeting point of a circle with a radius of 3, okay, and an angle of 225 degrees. So I can come out to this circle with a radius of 3, and then I can swing around, okay, to this angle that's 225 degrees. So that's going to put me right here. Okay, so this would be the point on this polar grid where we have 3 as the radius and 225 degrees as the directed angle. Okay, now there's obviously other ways that you could name this point. I'm going to get to this later on. Okay, you realize that you could swing around again 360 degrees, or you could actually rotate clockwise 360 degrees, or multiples of that. Okay, so we'll talk about that later on. All right, let's take a look at another example. So here we're given the rectangular coordinates. We have the negative of 2 times square root of 3, comma 2. So again, this is your x value, and this is your y value. So to get the r value, what are we going to do? Remember, this is equal to the square root of, you take the x value squared, so the negative of 2 times square root of 3, okay, being squared, and then plus, you're going to go ahead and take the y value squared. So 2 squared, let's just go ahead and write 4, okay? So if I square negative 2, I get 4. If I square the square root of 3, I get 3, okay? So this would be 4 times 3, which is 12. So let me go ahead and put a 12 in there. And 12 plus 4 is obviously 16. And the square root of 16 is going to be 4. Okay, so we have the r value. Again, that's pretty easy to get. When you consider theta, okay, you have to think about what quadrant you're in. So if my x value is negative and my y value is positive, that means I'm going to the left and I'm going up, right? So I'm going to be in quadrant 2. So theta is in quadrant 2. Okay, so always figure that out first. So then what I want to do is I want to think about, okay, well, the tangent of theta is equal to y, which is 2, over x, which is negative 2 times square root of 3. Let's go ahead and cancel this with this. And basically I have 1 over, you would have the negative of the square root of 3. Let's put the negative out in front, and then we'll put the square root of 3 over here. And then I'm going to rationalize the denominator, so square root of 3 over square root of 3. So this becomes the negative of the square root of 3 over 3. Now, I'm not going to use the negative because I want something in quadrant 1 when I use my inverse tangent function. So let me erase all of this, okay? And basically what I'm going to do is I'm going to say I want the inverse tangent of, let me go ahead and make this positive, so I'll say the square root of 3 over 3. If I punch that into my calculator, I'm going to get 30 degrees, okay? So the way this works, if I'm in quadrant 2, okay, and I want an angle with a reference angle of 30 degrees, I want to take 180 degrees and subtract 30 degrees away from that. So basically, my theta would be equal to 180 degrees minus 30 degrees, which is 150 degrees. Okay, so 150 degrees. And I forgot to put my 0 there, so let me put that in. So the polar coordinates are let me write this out. The polar coordinates will be what? It's your r value, comma, your theta value. So 4, comma, 150 degrees. So to plot this, so again, the point would be 4, comma, 150 degrees as polar coordinates. And again, all I'm going to do is I'm going to go out to a circle with a radius of 4, okay? And what I'm going to do from there is just swing around, okay, until I get to 150 degrees. Let's go ahead and plot that point right there, okay? So this is going to be 4, comma, 150 degrees. Again, plotting this on the polar grid. All right, let's take a look at an example where we have polar coordinates and we want to convert to rectangular coordinates. So first off, we have 6, comma, 75 degrees. Let's just plot this real quick. So again, what I want to do, I want to go out to a circle with a radius of 6. Okay, so right here. And then I'm going to swing around to an angle that's 75 degrees. So that's going to put me right there. Okay, so that's going to be my point 6, comma, 75 degrees. All right, so let's consider how to transform this into rectangular coordinates now. So remember, if we want to write this as x, comma, y, the relationship we talked about earlier is that x is equal to r times cosine of theta, and that y is equal to r times the sine of theta. So these are two things you need to memorize. You're going to use it basically all the time. Now, once we think about this, we have our r value of 6, so you might as well just put this as 6 in each case. Okay, so 6 and then 6. And then what is the cosine of 75 degrees and what is the sine of 75 degrees? So remember, this is not on your unit circle, okay? So what you can do is use identities, okay? We talked about this earlier in the course, to get an exact value, okay? If you punch it into your calculator, you get an approximation. So you could write 75 degrees as 45 degrees plus 30 degrees, okay? And you could use your cosine sum identity or your sine sum identity, depending on what you're working with, to get the exact value, okay? I'm just going to give this to you because we don't want to spend time working on something we already did. So essentially, the cosine of 75 degrees, I'm going to put some parentheses here, and I'll put it as the square root of 6 minus the square root of 2, and this is going to be over 4, okay? And then the sine of 75 degrees, again, I'm going to put, let me kind of slide this down a little bit so it's not in the way. I'm going to put this as, we'll have the square root of 6 plus the square root of 2, and this is going to be over 4, okay? So this is getting exact values. If you want to punch it in your calculator and approximate it, you can do that too. It's up to you. So let's go ahead and cancel this with this, okay? So this would basically be a 3, and this would be a 2, okay? And then from there, I would distribute this in. So I would have 3 times square root of 6. So 3 times square root of 6 minus 3 times square root of 2, and this is over 2, okay? So this is going to be your x-coordinate. Then here, this cancels with this. Again, this is the 3, and this is a 2. And then you're going to distribute that 3 into each. Okay, so let me put this as a 2. This would be a 3, and this would be a 3. Let me slide this down. So this would be 3 times square root of 2, okay? So if you want to write this as rectangular coordinates, you can go ahead and say that it would be 3 times square root of 6 minus 3 times square root of 2 over 2, and then comma. Let me erase this. This is all going to not fit. So let me slide this down a little bit so it all fits on the screen. And then over here, I'd have 3 times square root of 6 plus 3 times square root of 2, and then over 2. So kind of messy, kind of nasty. Again, your teacher might allow you to approximate it, so it might be a little bit quicker for you to do it that way. All right, let's look at one more example where we're going from the polar coordinates to the rectangular coordinates. So here we have negative 4, 120 degrees. So the r value, okay, is going to be negative 4, and the theta is going to be 120 degrees. So let's pause for a minute. When you get an r value that's negative and you're asked to plot this guy, it can be a little bit confusing, okay? When you get a theta value that's negative, that's pretty simple. We know that a negative angle just means I'm rotating clockwise, right? So let's deal with this r value that's negative first. Let's go to the polar grid, and let's first graph positive 4, 120 degrees, and then we'll think about what negative 4, 120 degrees would mean, okay? So if I step out to a circle here with a radius of 4, so let me go out here, and let me swing around, okay? And I'm just going to draw a little terminal ray. I'll do that the best that I can. I'm not a good drawer. But basically, that point's going to be right there, okay? So you'll notice that that point is on that terminal ray, okay? So this is going to be the 4, 120 degrees, okay? We know how to find that at this point, okay? Now, if I wanted to find negative 4, 120 degrees, all it means is that I'm basically going to reflect this point across this pole. Okay, so here's the pole right here, and if I reflect it across the pole, I'm basically going to go in the opposite direction. So I'm going to go this way 1, 2, 3, 4 units. So that's going to be right there. Okay, you can think about making a terminal ray here, and think about having the angle. Let's say I had the angle. I just start here and go all the way around. That would basically be a 300-degree angle. Okay, so negative 4, 120 degrees would represent the same point as 4, 300 degrees. And we're going to talk more about these different forms in a moment, okay? But for right now, you could see a few different ways that you could go about finding this. So let me go to a fresh sheet here where this is already plotted. So the first thing, I'm going to label this as negative 4, comma, I'm going to do 120 degrees, okay? I could have found this by going to 120 degrees like this, and then basically just instead of going forwards, I would just go backwards by 4 units. Okay, that's probably the easiest explanation. So I would just say, okay, I'm here, so I'm going to go 1, I'm going to go 2, I'm going to go 3, I'm going to go 4. So out to a circle that has a radius of 4, right? I'm just turning around and going backwards. That's what the negative 4 is basically telling me, okay? So that would be one way I could get to my point. Another way, and this might be helpful for you, you might want to plot 4, 120 degrees. So I got to 4 here, swing out to 120 degrees. So I'm going to be right there. So this is my 4, 120 degrees. And notice that if I wanted to swing over here, okay, I'm basically going to add 180 degrees to this angle. Okay, or I could subtract 180 degrees from the angle as well if I wanted to. So I could either say that this is going to be plus 180 degrees, which would be 300 degrees, or I could subtract away 180 degrees and say this is negative 60 degrees if I wanted to rotate clockwise, okay? But essentially, those are the ways that you could think about doing this. Once you graph these a few times, it becomes a little bit easier to work with in your mind. But just know if you have a negative R value, you're basically going to walk backwards. Okay, that's what it means. So let's go back and let's think about putting this into rectangular form. Okay, so we know again that our X value is equal to, we would have the R value, which is -4, times the cosine of 120 degrees, and the Y value is -4 times the sine of 120 degrees, okay? So we know that 120 degrees is going to be in quadrant 2. It's got a 60-degree reference angle, and the cosine of 60 degrees is going to be a half, okay? But cosine is negative, okay, in quadrant 2, so this would be -1/2. So times -1/2, so of course this would be +2. So the X value is +2, very easy to find. The sine of 120 degrees, again, a 60-degree reference angle, sine is positive in quadrant 2. So the sine of 60 degrees is square root of 3 over 2. So this is going to be times the square root of 3 over 2. I can cancel this with this, and I would have the negative of 2 times square root of 3. So -2 times square root of 3. So then my rectangular coordinates would be 2, -2 times square root of 3. Okay? So basically, I want to go from here into our next point, which is talking about alternative forms for coordinates of a point in polar form. So for a given point in the rectangular coordinate plane, you're going to have an infinite number of pairs of polar coordinates. So sometimes your teacher will say, give me, 4 examples of other polar coordinates that are the same as this polar coordinate I'm giving you. Sometimes they want a general formula. So I'm just going to give you the general formula here, and then you can apply that based on the example you get, okay? So the first one is pretty easy to understand. If we have some r comma theta, this is the same as if I said r comma, and then your theta plus 360 times n degrees, n is just any integer, or theta minus 360 times n degrees. Now, the plus or minus here is given in some books. You really don't need it. You could just put plus because n is any integer, so you can make it positive, you can make it negative, you can do whatever you want, okay? But some books will put plus or minus, others will just put plus. If you go back to, let's say, this guy right here, where we have 4, 120 degrees. Well, if you think about it, I could add 360 degrees to this, and I could say, well, also the same point could be located if I said 4, this would be 480 degrees, right? Because basically, from here, I would swing around another 360 degrees, and it'd be right back to that same point. I could add 360 degrees again and get to 840 degrees. Then I could do it again and again and again. And the same thing is true if I subtracted 360 degrees away from 120 degrees. So some other coordinates would be something like 4, -240 degrees. Okay, so that would all locate the same point. Okay, so now let's look at this second formula. This one is a little bit more challenging to understand. But remember, if you have r and you have the negative of r, remember, when you think about the negative of r, you're basically going to be walking backwards. Okay, so this is what this is related to. So again, you have this theta, whatever your angle is, plus or minus, you're going to have this 180 degrees times this quantity. So let me distribute this out. So I'm going to put plus or minus, and I'll go ahead and say you'll have your 180 degrees times 2n. So let's say this is, we'll say 360, we'll say n degrees. And then I'll say plus, I'll go ahead and say do my 180 degrees like this, okay? So you could have positive or you could have negative. You're going to see that you can actually drop the plus or minus here as well. I'll go through some examples and prove that to you. Most books will just write this with a plus sign, but others put plus or minus, okay? So it's right either way. So if we go back and we think about alternative ways to locate this point. Remember, this was -4, 120 degrees, okay? So all we're saying is that we could have done the negative of this number, so that's 4, and then I could add or subtract 180 degrees to this. So if I add 180 degrees, I would be at 300 degrees, okay? So in other words, I could have gone out to right here, and then I could have swung by 180 degrees this way, right, to get to 4, 300 degrees, or I could have started there, and I could have swung 180 degrees this way. This would be clockwise, so that would be me subtracting 180 degrees. So I could have also said this is 4, if I subtract 180 degrees from this, I would get -60 degrees. Now, once I've added or subtracted the 180 degrees, I could then swing by multiples of 360 degrees, right? Either positive or negative. So that's where these formulas are coming from, because from here I could say, okay, well, this is 4, 300 degrees plus 360 degrees would be 660 degrees. Okay, so that's another way to locate that point. So in other words, I could have started here, and I could have swung around 180 degrees, okay, and then swung around another 360 degrees to get to that same point, okay? Also, what I could have done, I could have started at 4 comma negative 60, and I could subtract away another 360 degrees, which would be negative 420 degrees. Again, another way to locate the same point. So there's a lot of different ways you could have done this. So again, we put this into this nice little convenient formula, okay? So basically it relies on the fact that you're first adding 180 degrees, and then from there you could add 360 degrees and then times some integer n. That could be positive, it could be negative, it could be whatever. Again, you see this plus or minus here, but you could drop that and just put a plus, and I'll show you that in the example. All right, so let's just look at an example here. So we have the polar coordinates 3 comma 240 degrees, and what I'm going to do is ask you for a formula for all the pairs of polar coordinates that describe the same point. Again, your example might be different. They might say find them within this certain range. You just have to apply to that, okay? So what I'm going to do here is first start by saying, okay, the 3 would be the same. And what I would do here is I would add 360 times n to this, right? So the formula you saw was theta plus or minus 360, and you would do n degrees, okay, like this. Well, theta is 240 degrees, so let me put that in there. So 240 degrees, and then plus or minus your 360 times n. Well, I don't need the plus or minus because I can get anywhere I want to go by just varying n, right? N is any integer, so it could be positive, it could be negative. So again, you can put plus or minus, it's not wrong, but really most books will just put plus. You don't need the minus. So let's go ahead and get rid of that. Okay, so the next one is a little bit more challenging to understand. So remember, you would put the negative of whatever this number is. So in this case, it's 3. So I'm going to go ahead and put negative 3. And then I'm going to put a comma. And let me go through and work out the two different scenarios. So I'm going to go ahead and say I have 240 degrees. Okay. Then I'm going to go plus. Remember, you're going to have your 180 degrees. And then you're going to have plus your 360, okay, n degrees. So this is basically where I'm swinging 180 degrees, and then from there I can add multiples of 360 degrees. I'm also going to do this with the minus sign to show you it comes out the same. So let me close this real quick. Negative 3 comma, I would do 240 degrees, and then minus 180 degrees, and then minus 360 n degrees, okay? So basically, for this one, 240 degrees minus 180 degrees would be 60 degrees. Okay, so this would be 60 degrees. And then let me just tighten this down a little bit. We're going to end up erasing this one, so it doesn't really matter. Then this one, 240 degrees plus 180 degrees is 420 degrees. Okay, so 420 degrees. And if you think about it, 420 degrees, if I subtract off 360 degrees, this is going to be coterminal with 60 degrees. So really, I could just put this as 60 degrees, okay, and just slide this down. And now we want to think about this. Do I need the plus or minus here? No, because I can get wherever I want to go by just plugging in different integers for n, right? If I want to do negative, if I want to do positive, I'm allowed to plug in whatever I want there as long as it's an integer. So I can go ahead and get rid of this, okay, and just list it with the plus sign. Again, if you want to put plus or minus, it's not wrong, but it's just overkill, right? So I'm going to list this as my answer. So 3 comma 240 degrees plus 360 n degrees, and negative 3 comma 60 degrees plus 360 n degrees.